Hello! In this video, we're going to tackle what looks like a tricky equation. Our goal is to solve the equation x squared plus the square of x over the quantity x plus 1 minus 3 equals 0. We're looking to find the value or values of x that make this equation true. At first glance, this might seem complicated because of the fraction and the squared terms. However, we can solve this using a technique called substitution. This method will allow us to simplify the equation into a much more familiar form. So, by the end of this video, you will be able to solve complex-looking equations by identifying key components and simplifying them through substitution. Our first step is to rearrange the equation to group similar terms. Let's start with our original equation. We have x squared plus the quantity x over x plus 1 squared minus 3 equals 0. Let's move the constant term 3 to the right side of the equation. This gives us x squared plus x over x plus 1 squared equals 3. Now let's focus on the term x over x plus 1. We can rewrite this by adding and subtracting 1 in the numerator. This gives us the quantity x plus 1 minus 1 all over x plus 1. This might seem like a strange move, but it's a very helpful algebraic trick. Now we can split this into two separate fractions. We get x plus 1 over x plus 1 minus 1 over x plus 1. The first term, x plus 1 over x plus 1, simplifies to 1. So, our expression becomes 1 minus 1 over the quantity x plus 1. We have successfully rewritten x over x plus 1. Now, let's substitute this new expression back into our original equation. Our equation is now x squared plus the square of the quantity 1 minus 1 over x plus 1 equals 3. This looks a little cleaner. Okay, we've done some initial simplification. Now here's where the substitution comes in. Let's look at our equation again. We have x squared plus the square of the quantity 1 minus 1 over x plus 1 equals 3. Notice the term 1 minus 1 over x plus 1. Let's define a new variable, u, to represent this entire expression. Let's set it equal to 1 minus 1 over x plus 1. With this substitution, our equation becomes much simpler. It simplifies to x squared plus u squared equals 3. This is a much more manageable equation than what we started with. But how does this help us? We've just introduced a new variable. To solve this, we need to find another relationship between x and u. We can get this by rearranging our substitution equation. Let's start with u equals 1 minus 1 over x plus 1. We have u equals 1 minus 1 over x plus 1. If we solve this for 1 over x plus 1, we get 1 over x plus 1 equals 1 minus u. And if we solve for x plus 1, we find that x plus 1 equals 1 over the quantity 1 minus u. Finally, we can find an expression for x in terms of u. X equals 1 over the quantity 1 minus u minus 1. This is our second important equation. Now we have a system of two equations with two variables, x and u. This is exactly what we need to solve for x. Here are our two equations. Our first equation is x squared plus u squared equals 3. And our second equation is x equals 1 over the quantity 1 minus u minus 1. The next step is to substitute the expression for x from the second equation into the first equation. This will eliminate x and leave us with a single equation in terms of u. Substituting, we get the square of the quantity 1 over 1 minus u minus 1 plus u squared equals 3. Let's simplify the term inside the parentheses. We can find a common denominator. 1 over 1 minus u minus 1 becomes 1 minus the quantity 1 minus u, all over 1 minus u. This simplifies to u over 1 minus u. Now we can substitute this simpler expression back into our main equation. This gives us the square of u over 1 minus u plus u squared equals 3. Let's expand the squared term. We get u squared over the square of 1 minus u plus u squared equals 3. We're getting closer to a polynomial equation. Our goal now is to solve for u. Let's start by getting rid of the fraction. We have u squared over the square of 1 minus u plus u squared equals 3. To clear the denominator, we'll multiply the entire equation by the square of 1 minus u. This gives us u squared plus u squared times the quantity 1 minus u squared equals 3 times the quantity 1 minus u squared. Let's expand the squared term on the right side. 1 minus u squared is 1 minus 2u plus u squared. So the right side becomes 3 minus 6u plus 3u squared. Let's also expand the term on the left side. u squared times 1 minus 2u plus u squared gives us u squared minus 2u cubed plus u to the fourth. Now, let's put it all together. The equation becomes u squared plus u squared minus 2u cubed plus u to the fourth equals 3 minus 6u plus 3u squared. Combining like terms on the left side, we get 2u squared minus 2u cubed plus u to the fourth equals 3 minus 6u plus 3u squared. Finally, let's move all terms to the left side to get a standard polynomial form. This results in u to the fourth minus 2u cubed minus u squared plus 6u minus 3 equals 0. This is a quartic or fourth degree equation. Solving a quartic equation can be very difficult. However, this particular equation has a special structure that allows us to find its roots by testing integer factors of the constant term 3. Let's list the possible rational roots using the rational root theorem. We test the divisors of 3. The divisors are plus or minus 1 and plus or minus 3. Let's try plugging in 1 for u. 1 to the fourth minus 2 times 1 cubed minus 1 squared plus 6 times 1 minus 3 equals 1 minus 2 minus 1 plus 6 minus 3. This simplifies to 1. Since it's not 0, 1 is not a root. Now let's try 3. 3 to the fourth minus 2 times 3 cubed minus 3 squared plus 6 times 3 minus 3 equals a 1. Minus 4 minus 9 plus 18 minus 3. This equals 33. So 3 is not a root. Let's try 1. 1 to the fourth minus 2 times 1, cubed minus 1, squared plus 6 times 1 minus 3 equals 1 plus 2 minus 1 minus 6 minus 3. This gives 7, not a root. Finally, let's try 3. 3 to the fourth minus 2 times 3, cubed minus 3, squared plus 6 times 3, minus 3 equals 81 plus 54 minus 9 minus 10 minus 3. This equals 105, not a root either. It seems the rational root theorem isn't working for us. This means the roots are either irrational or complex. Let's look for a different pattern. Let's re-examine our quartic equation. We derived it from the system of equations. X squared plus u squared equals 3 and x equals u over 1 minus u. Let's consider a possible relationship between x and u. What if x and u were roots of a single quadratic equation? Let's assume there is a quadratic equation whose roots are x and u. Let's call this variable t. The quadratic equation would be of the form t squared minus sum of roots t plus product of roots equals 0. Let's calculate the product x times u. X times u equals u squared over the quantity 1 minus u. Let's calculate the sum x plus u. X plus u equals u over 1 minus u plus u. Finding a common denominator, we get u plus u times 1 minus u all over 1 minus u. This simplifies to 2u minus u squared all over 1 minus u. Now let's compare the sum and product. Notice something interesting. If you look closely, the sum of the roots is just the product of the roots times 2. X plus u equals 2 times the quantity u squared over 1 minus u, which means x plus u equals 2 times x times u. Let's verify this using our original substitution. We know that x plus 1 equals 1 over 1 minus u. This means x equals 1 over 1 minus u minus 1, which simplifies to u over 1 minus u. So our relationship x plus u equals 2xu is correct. This gives us the relationship x plus u equals 2xu. We now have 3 key pieces of information to solve this problem. These 3 equations form a system that we can solve. Our system is 1. X plus u equals 2xu. 2. X squared plus u squared equals 3. 3. U equals 1 minus 1 over x plus 1. These 3 equations are all connected and will lead us to the solution. Let's work with the first 2 equations. Remember that x squared plus u squared can be rewritten. It's equal to the square of the quantity x plus u minus 2xu. This is a very useful algebraic identity. Now we can substitute our first equation, x plus u equals 2xu, into this identity. We will also substitute the value from our second equation, x squared plus u squared equals 3. This gives us 3 equals the square of the quantity 2xu minus 2xu. Let's call this our combined equation. It only involves the product xu. Let's define a new variable for simplicity. Let's say v equals x times u. If v equals xu, our equation becomes 3 equals 4v squared minus 2v. This is a simple quadratic equation in v. To solve it, we can rearrange it to the standard form, x squared plus bx plus c equals 0. We get 4v squared minus 2v minus 3 equals 0. We can solve for v using the quadratic formula. We've arrived at a quadratic equation for v. Let's solve it using the quadratic formula, which is v equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Our equation is 4v squared minus 2v minus 3 equals 0. Here a equals 4, b equals negative 2, and c equals negative 3. Substituting these values into the formula, v equals 2 plus or minus the square root of negative 2 squared minus 4 times negative 3 all over 2 times 4. This simplifies to 2 plus or minus the square root of 4 plus 48 all over it. We get 2 plus or minus the square root of 52 all over a. The square root of 52 is the square root of 4 times 13, which is 2 times the square root of 13. We can divide the numerator and the denominator by 2. This gives us our two possible values for v, 1 plus the square root of 13 over 4, and 1 minus the square root of 13 over 4. Remember, v is equal to x times u. So we have found the two possible products for x and u. X times u equals 1 plus the square root of 13 over 4, or x times u equals 1 minus the square root of 13 over 4. We now have two cases to consider, corresponding to the two values of v we just found. Let's start with the first case. Case 1, v equals xu equals 1 plus the square root of 13 all over 4. We also have the identity we discovered. X plus u equals 2q. Using our value for xu, we find that x plus u equals 2 times the quantity 1 plus the square root of 13 over 4, which simplifies to 1 plus the square root of 13 over 2. Now we have the sum and product of x and u. This is exactly what we need to form another quadratic equation. The quadratic equation with roots x and u is t squared minus the sum of the roots t plus the product of the roots equals 0. Let's substitute our values for the sum and product. We get to squared minus the quantity 1 plus the square root of 13 over 2 times t plus the quantity 1 plus the square root of 13 over 4 equals 0. To make this easier to work with, let's multiply the entire equation by 4 to clear the denominators. This gives us 4t squared minus 2 times the quantity 1 plus the square root of 13 times t plus 1 plus the square root of 13 equals 0. Let's solve for t using the quadratic formula. Here a is 4, b is negative 2 times 1 plus square root of 13, and c is 1 plus the square root of 13. The quadratic formula gives us t equals 2 times the quantity 1 plus the square root of 13 plus or minus the square root of the discriminant, all over 8. Let's simplify the term under the square root, called the discriminant. The discriminant simplifies to 4 times 13, which is 52. So the square root of the discriminant is the square root of 52, or 2 times the square root of 13. Wait, something is wrong here. Let's double-check the algebra. Let's recalculate the discriminant. It's 40 minus 8 times the square root of 13. This result is complex, meaning our initial assumption might be incorrect or I've made an error. Let's re-examine our reasoning. The roots t are x and u. If we're looking for real solutions for x, then t must be real. A complex discriminant means t is complex. Let's take a pause. This discriminant is positive, not negative. My previous statement was incorrect. The square root of 40 minus 8 times the square root of 13 is a real number. It's not a complex result, so we can continue. The discriminant is 40 minus 8 times the square root of 13. Since this is positive, we will get 2 real roots for t. Let's return to our system of equations. X plus u equals 2xu, and x squared plus u squared equals 3. Let's try solving this in a different way, which might be more intuitive. We can see that x squared plus u squared equals 3. We also know that x plus u squared is x squared plus 2xu plus u squared. So mat to x plus u, 2l 3 plus 2xu. From the first equation, we know xu equals xu 2. Substituting this in, x plus u2 equals 3 plus 2 times x plus 2, which simplifies to x plus u2 equals 3 plus x. Let's make a substitution here. Let s equal x plus u. We get s squared equals 3 plus s, which we can rearrange to the quadratic s squared minus s minus 3 equals 0. Using the quadratic formula, s equals 1 plus or minus the square root of 13, all over 2. We have two possible sums, and we must check them against our original problem. This gives us two possible values for the sum s, which is x plus u. Now, let's consider the case where s equals x plus u equals 1 plus s cart 13, 2. We have x plus u equals 1 plus the square root of 13 over 2. Also, from our first equation, xu equals s over 2, which is 1 plus the square root of 13 over 4. Let's form a quadratic equation with roots x and u. Let the variable be t. We get t squared minus the quantity 1 plus the square root of 13 over 2 times t plus the quantity 1 plus the square root of 13 over 4 equals 0. Notice this is the same quadratic equation for t that we found before, whose roots are x and u. Now let's consider the case where s equals x plus u equals 1 minus s squared 13, 2. Here, x plus u is 1 minus the square root of 13 over 2, and xu is 1 minus the square root of 13 over 4. These are our new sum and product. Let's form the new quadratic equation for t. The equation is t squared minus the quantity 1 minus the square root of 13 over 2 times t plus the quantity 1 minus the square root of 13 over 4 equals 0. The roots of this new equation are x and u. So we have two quadratic equations for t. The roots of each equation represent a pair of values, x, u, that solve our system. Let's first ensure that both solutions for t are real. This requires checking the discriminant for each equation. Remember, the first equation's discriminant was 40 minus 8 times the square root of 13. The square root of 13 is between 3 and 4, so 8 times the square root of 13 is less than 32. Thus, 40 minus 8 times the square root of 13 is positive. This means real roots x and u exist for the first case. For the second equation, the sum is 1 minus sqrt 13, 2, which is negative. The product is 1 minus sqrt 13, 4, which is also negative. The discriminant is sum tier 2, 4 product. A negative product means the discriminant will be positive, so we also have real roots for the second case. It is 13, 2 plus 13 to 1. 13, 13 plus 12. Equals 26, there's 2 basket to 13, 0. Both cases lead to real roots for x and u. Now let's find the values of x. For each quadratic for t, the roots are x and u. From the definition u equals 1 minus 1 over x plus 1, we can see that u cannot be equal to 1. Also, since u is a root of the quadratic, if a root equals 1, then the constant term must be 0. The constant terms are 1 plus sqrt 13 over 4 and 1 minus sqrt 13s over 4. Neither of these is 0, so u does not equal 1 in either case. This means that for each quadratic equation, the two roots for t are x and u. They are distinct from each other, so we have two pairs of x-u solutions. For our original equation, we only need the values of x. The values for x will simply be the two roots of one quadratic and the two roots of the other. So we expect a total of 4 real solutions for x. Let's summarize what we've accomplished. We started with a complex equation and, through substitution and algebraic manipulation, simplified it into a system of 2 related quadratic equations. We found 2 quadratic equations for a variable t, whose roots are the pairs x, u. The roots of the first equation, let's call them x1 and u1, form one solution. The roots of the second equation, x2 and u2, form another. We've shown these roots are all real. The roots of the first quadratic are x1 equals the quantity 1 plus the square root of 13 plus the square root of 40 minus 8 times the square root of 13, all over 8. And x2 is the same, but with a minus sign before the second square root. So x equals 1 plus the square root of 13 plus or minus the square root of 40 minus 8 times the square root of 13 all over e. The roots of the second quadratic give two more solutions. Let's call them x3 and x4. These are 1 minus the square root of 13 plus or minus the square root of 26 minus 2 times the square root of 13 all over e. The final step is to check for domain restrictions. The term x over x plus 1 requires that x not be equal to 1. The two sets of four solutions we found do not include 1, so they are all valid. So we have found all four real solutions for x. You have now learned how to solve a complex equation by using a system of equations, substitution, and the properties of sums and products of roots. Thank you for watching.